In this section, we're going to discuss the equilibrium constant and equilibrium expressions. In the late 1800s, Cato Goldberg and Peter Wagg determined what is known as the law of mass action, which states that for a simple one-step reaction, the rate of the chemical reaction is proportional to the concentrations of the solutions or the partial pressures of the gases involved in the reaction. So, given a balanced chemical reaction comprised of solutions, the reaction rate will be highest for those reactants or products with the greatest concentration. Given a balanced chemical reaction comprised of gases, the reaction rate will be highest for those reactants or products with the highest partial pressure. This law only applies to single-step reactions or the elementary step within multi-step reactions. Equilibrium constant. At equilibrium, the forward and reverse reaction rates are equal. The law of mass action led to an understanding for simple one-step reactions and elementary steps how each of those rates are affected by the concentration of solutions or partial pressures of gases. It led to the development of the equilibrium constant, or K. K leads to a number of insights about how a reaction will proceed. For more complicated reactions, K cannot be calculated based on coefficients. It must be experimentally measured. When calculating K, we will be assuming it is a simple one-step reaction. Chemical equilibrium. All right, let's look at a reaction we've talked about previously, where we have N2O4 gas, colorless, and NO2 gas, which is a brown gas, and we have an equilibrium, dynamic equilibrium between the two gases. We have the forward reaction, where N2O4 is producing NO2, and the reverse reaction, where NO2 is producing N2O4. The rate of this reaction is proportional to the reactant concentrations. The forward reaction I've isolated here, and its rate is equal to K, the rate constant of the forward reaction, times the concentration of N2O4. Here's the reverse reaction, and its rate law is K, the rate constant of the reverse reaction, times the concentration of NO2 squared. So we need to take those rate laws that we discussed in the previous slide and derive what's known as the equilibrium constant. So chemical equilibrium is established when the rate of the forward reaction equals the rate of the reverse reaction. Therefore, at equilibrium, the two rate laws are equal. So the rate of the forward reaction is equal to the rate of the reverse reaction. And so I've substituted here the rate law, K, forward rate constant times concentration of N2O4 equal to reverse rate constant times concentration of NO2 squared. And I've just solved here. I've made a ratio of the rate constant for the forward reaction to the reverse reaction. And I get the concentration of NO2 squared over N2O4. The ratio of the rate constants is known as the equilibrium constant K. So I have this ratio of the forward rate constant to the reverse rate constant, which is equal to KEQ, the equilibrium constant, or sometimes it's just referred to as K. So this is the same ratio we derived on the previous slide, concentration of NO2 squared over concentration of N2O4. Now, in our kinetics unit, we had talked about how these rate laws had to be derived experimentally. And now in this unit, we're using these stoichiometric coefficients. So here's an important thing to note. The K, the equilibrium constant, depends on the stoichiometric coefficients, is only true for one step and elementary steps. So we're going to assume that when asked to calculate K from a reaction equation, we're only going to be provided reactions for which this assumption is correct. Equilibrium expressions. For one-step equations and elementary steps, the equilibrium constant expression can be written from a balanced chemical equation. So if this is my forward reaction, reactant A and B, capital A and B, product C and D, capital C and D, with these lowercase stoichiometric coefficients, the general format for the equilibrium expression is the equilibrium constant K, or Kc. This C stands for molarity or concentrations. We're talking about concentrations of reactants and products. Is the ratio of the concentration of each product, so in this case C and D, raised to its stoichiometric coefficient, divided by the concentration of each reactant A and B raised to its stoichiometric coefficient. Okay, so concentration of C to the C power times concentration of D to the D power divided by concentration of A to the A power times concentration of B to the B power. And again, Kc just is the concentration equilibrium constant, the same as K, and the values are in molarity or concentration. Pure solids and liquids, so pure solids, something in a reaction that says solid or liquid, are not included in the calculation of the equilibrium constant. And that's because while their amount may change, the amount of the solid or the amount of the liquid may change, their concentration remains the same during the reaction. Okay, so we're talking about changes in concentration for solutions. So we're talking about aqueous solutions. And then we can similarly, or gases. We're going to talk a lot more about gases in the next section, but when we're talking about concentration changes here, we're talking about solutions and gases. Example 1, equilibrium constant. Write an expression for the equilibrium constant of this reaction. So the first thing I'm going to do is just isolate our products, and we're going to leave out this H2O because it's a liquid. And then our reactants, we have O2 and CH4. So K is equal to, it's the ratio of the concentration of the products raised to their stoichiometric coefficient. There's a 1 there, we don't have to write, okay? The ratio of products to reactants. So the concentration of, so you have CH4 and then O2 to the second power, okay? So there's our equilibrium expression for this reaction. If I go ahead one slide, we place the concentrations of the products over the concentration of the reactants and raise the concentrations to the power of the coefficients. We have a square there. Ignore pure liquids and solids. So notice the liquid H2O does not appear in the expression because solids and liquids are not included in the calculation of K. Example 2, equilibrium constant. Write an expression for the equilibrium constant of this reaction. So we have two products that are aqueous, and then we have one reactant that is a solid. So we're not actually going to include that in the equilibrium expression. So you can say K is equal to the concentration of the products, okay, and the Ag plus silver ion has a coefficient of 3, so I raised it to the 3 power, and then phosphate PO43 minus has a coefficient of 1, so raised to the 1 power, and then there's nothing on the bottom, right? There's nothing there because we don't include this in the expression, okay? So this is our final equilibrium constant expression right here. Only products appear in this expression since the only reactant is a solid, which is excluded. So we have KEQ, or K equals silver ion concentration to the third power times the concentration of the phosphate ion.